The second lecture on advanced quantum mechanics. Today we shall continue our discussion on relativistic quantum mechanics. Today our topic will be the Dirac's theory, a part of the Dirac's theory, and the Dirac's theory will be completed by in the next lecture. By in the earlier class we have you introduced Klein-Gordon equation, the first relativistic equation, which starts from the relativistic energy expression E square is equal to m square c to the power 4 plus c square p square, where m is the rest mass energy of the particle, and we got the Klein-Gordon equation from it, and we found that the probability current, the probability density rho is of the form del T of is not essentially positive. This was the main problem with Klein-Gordon equation. Furthermore, this equation, as will be apparent afterwards, that contains no spin term, so it in common days it is known as the relativistic equation for spin zero particles. The energy spectrum as obtained from Klein-Gordon equation is that this is the K, so the energy increases from mc square onwards with the increase of K value, and it decreases below minus mc square with increasing K values. So this is the energy spectrum that we obtain from Klein-Gordon equation. Dirac identified with the problem with Klein-Gordon equation is due to the fact that the energy relation is quadratic, and Dirac assumed a linear Hamiltonian for the system. As per Dirac, a British scientist Dirac, he assumed the Hamiltonian describing a free particle to be mc square beta plus c times alpha dot p, and if we call operator, since they are operators, and since m0 c square, none of them are dynamical variables, so in that sense beta has to be an operator. And the Schrödinger equation, or we prescribe Schrödinger equation, then H psi is equal to E psi, which gives us the equation that E minus mc square beta minus c, this we write summation over I is equal to 1 to 3 alpha I pi. For the sake of brevity, we are not putting the operator sign, that is the hats are not written over here, and this is equal to psi times this is equal to 0. What could be the possible nature of alpha and beta? Note that this is a free particle Hamiltonian, so this should not include any force term. And if we have space-time dependence of the quantities alphas and betas, if we have alpha beta has space or time dependence or both, then this could lead to a force term, because the Hamiltonian will this quantity will change from point to point and from time to time, so that would include a force term. So we conclude that beta and alpha I do not have any space-time dependence. do not have any space-time dependence. That is to say, they are constant quantities. They may we are not right now. I am not saying anything more about alpha beta. Only thing that as they do not have any space-time dependence, they commute with any dynamical variable, say p. Each of the component of alpha and beta commutes with p and energy operator. And to get some idea about the quantities about the alpha beta, we multiply this quantity by this one, E plus mc square beta plus c summation over j alpha j p j, and then this quantity. If we multiply it, these are two trinomials, and if we multiply this, I have firstly e square term, this multiplied by this, and if we multiply this by mc square e beta, then we have minus c e summation over I alpha I pi. These are the three terms. When this we multiply each of the term of the second trinomial by the first one of the first one. Then we have plus mc square beta times e, as we have argued that beta commutes with e, beta and alpha commutes with every dynamical variable, so we can write it as we write it still beta e. Then then we have this term minus m square c to the power 4 beta to the power 4. Then we have this term mc cube beta summation over alpha I pi. Then we have three terms originating from this. The first term is C plus C E summation over alpha I pi. Here we have assumed that note that first alpha appears, then alpha p appears, then E appears, and as alpha commutes with E or any other variable, we have changed the order here. Then this is mc cube summation over j alpha j p j beta, and finally we have minus c square summation over j alpha j p j summation over I alpha I p I psi is equal to 0. First thing, you note these two quantity mc square e beta, mc square beta e. They are of opposite sign, and since e beta is equal to beta e, they cancel in pair. Then we have another term. This is this term and this term. The term underlined, the double underlined. These two terms also cancels out. So we are left with 5 terms. Sorry, it is E square. E square, then we have minus m square c to the power 4 beta square. C to the power 4, it was beta square. First, second, third, fourth, fifth term. The fifth term originates by when we multiply this with this, so m square c to the power 4 beta square. Then we have two terms, this term and this term. Both are negative, mc cube. We write minus mc cube summation over, say, I. First term is beta alpha I, and second term is, since this beta commutes with p, we can rewrite it alpha j beta, or we write alpha I beta pi. Note that this term, this was sum alpha j pj beta, this dummy variable. Since this does not contains any other dummy variable, I write it alpha I pi beta. Since p and beta commutes, we write it alpha I beta pi. So this is the term. Now we come to this term. So we have considered, initially we had 9 terms, of which 4 cancels out. So we were left with 5 terms. So this is 1, 2, 3, 4, and only the last term is left over to consider. We recall that summation over alpha j pj sum over j times sum over I alpha I pi. This is actually alpha x px, alpha y py, alpha z pz multiplied by alpha x px, alpha y py plus alpha z pz. Then this first term is alpha x square px square. Then we have this such terms alpha y square py square, alpha z square pz square. Here we have again assumed that alpha alpha I pj is equal to pj alpha I, as we argued at the beginning, and the rest of the terms is alpha x alpha y plus alpha y alpha x px py, again px py commutes this term. When we multiply this with this, we get alpha x alpha y, and when we multiply this term with this, we get this term. Alpha y alpha z plus alpha z alpha y So we write this thing and we had minus c square common, and then we have alpha x square px square plus alpha y square py square alpha z square pz square plus this part we write as alpha x alpha y anti-commutator. In commutator bracket we write in commutator AB commutator is generally written as AB minus BA. Operator signs are there. And in anti-commutator notation this expression is AB plus BA. This is the anti-commutator notation which we have introduced here. So this is plus alpha x alpha y anticommutator px py plus alpha y alpha z anticommutator py pz plus alpha z alpha x anticommutator pz px operating on psi is equal to 0. If you use anti-commutator notation, then this can also be written as beta alpha I anti-commutator. So we change this term also. This is the Hamiltonian. If we compare this expression with the corresponding Klein-Gordon expression for a particle, free particle moving in 3D, we find that it is E square minus m square c to the power 4 minus c square p square, c square p. By p square we mean px square, py square, pz square operating on psi is equal to 0. If we compare this Dirac equation with the Klein-Gordon equation, few things comes. Oh, I have missed beta square term. mc to the power 4 beta square. This beta square term I am missing. And the sign was mc cube. It was the. So we see by comparing, we see that beta square, compare these two terms, beta square is 1. This is c square p square, so alpha x square is equal to alpha y square is equal to alpha z square. They are all have square of them are, and the anti-commutator beta alpha I anti-commutator is 0 and alpha I alpha z anti-commutator 0. So we see that alpha i's and betas are quantities whose anti-commutators are 0, so they cannot be pure numbers. They are operators because if we have two numbers AB and BA, they are same, so we get this is 2AB. So if this could be 0, then either A should be 0 or B should be 0. But here we see that if B is equal to beta is equal to 0, then this term disappears from the expression, and if any one of the alpha x square is 0, then this term will disappear. So we conclude that they cannot be scalars. Null scalars, rather they are matrices. So our aim is to find out 4 matrices. Since this Hamilton, it is Hermitian, the Hamiltonian is Hermitian, the right hand side p's are Hermitian, so we need to have operators beta and alpha I. They are Hermitian operators, that is they are square operators or square matrices, such that all these 4 quantities anti-commute in pairs. So alpha i's and beta are Hermitian and anti-commutes in pair. commutes in pairs. Furthermore, they have determinant plus minus 1. This property, as their squares are 1, the squares are 1, the eigenvalues are of alpha i's and beta are only plus minus 1. This is from the fact that their squares are an identity operator. This 1 means they are identity operator. So since their squares are equal to identity operator, then their eigenvalues can have only plus minus 1 values. Now, another thing is that they anti-commute in pairs as alpha I square is equal to beta square is equal to identity operator. And furthermore, the trace of alpha I is equal to 0 is equal to trace of beta. This follows from the anti-commuting property. With a little bit of matrix algebra, we can see that they will have 0 trace. So trace is the sum of the diagonal values, and the diagonal values can be only plus minus 1. So we conclude that the dimensionality of the matrices alpha and beta are even only. That is, the rank of alpha i's and beta are even only. That is, they could be a 2 by 2 matrix or 4 by 4 matrix or 6 by 6 matrix. They cannot be 3 by 3 matrices. Now, we recall that the Pauli already introduced the matrix which bears his name, known as Pauli spin matrices. They are, before going to Pauli's matrix, let me summarize the fact that and they are Hermitian matrices of even rank. Now, we know from beforehand that there were Pauli spin matrices were introduced. They are 3 2 by 2 matrices, sigma x, sigma y, and sigma z. The Pauli spin matrices were like this. The Pauli spin matrices are this: sigma y is equal to 0 minus I 0, and sigma z is equal to 0 1 1 0 0 minus 1. They have the property that sigma I sigma j, they anti-commute in pair, and furthermore that sigma I square is identity matrix. So the basic requirement that we were facing with alpha i's and beta are made by Pauli spin matrices. One thing is of interest to know that the commutator of sigma j is equal to twice I h cross epsilon I j k sigma k. Now we first check whether sigma I can be related to alpha I or not. You notice that we need 4 independent matrices, but these 3 matrices sigma I with I is equal to 1 2 3 and I2, this is 1 0 0 1, forms a complete basis in 2 cross 2 space. So any matrix can be written as a combination of this. So if we could relate this sigma i's with alpha I, then beta is no more an independent matrix, and beta cannot be unit matrix. So the beta cannot be a unit matrix is apparent from here, because had beta been an unit matrix, then anti-commutator would be simply twice alpha I, which cannot be 0. So beta cannot be unit matrix. So we see that this is not possible to have the representation of alpha i's and beta in 2 cross 2 space. The conclusion is alpha i's and beta are not 2 cross 2 matrices. So what to do? Then only possibility is that they could be a matrix in 4 cross 4 space. Dirac assumed Dirac's representation, this is known as Dirac's representation. Dirac assumed quite arbitrarily that beta is a diagonal matrix. So it is a matrix 2, this is a null matrix of order 2, this is another null matrix of order 2, and this is an unit matrix of order 2. This was Dirac's assumption. So if we write it explicitly, this becomes 1 0 0 1 0 0 . This is the matrix for beta as per Dirac's choice.